We are Angela Patiño and Angie Carvajal, and we are going to explain the next exercise. We have 4 bars with a cross section of 36 millimeters and 8 millimeters, and each of the bars has 2 links with a 16 millimeters in diameter. Now we need to calculate the maximum normal stress of the bar BD and the bar CE. But first, it's important to know that when we apply the 20 kilonewton force upwards, the, the bars BD and CE will work differently because the bar BD will be in tension with a force in this way, and the bar CE will be in compression with a force to this way. Now, the normal method or the formula that we use to calculate the normal stress is this one right here. That will be equal to the force in BD and to the area in BD. But we need to remember that they are asking about the maximum normal stress in the bar BD and in the bar CE. So we need to find the section of each of the bars where it found the most stress. So in case of the bar BD, this will be in the links because of the tension force, and in the bar CE, this will be in the center of the bar because of the compression force. Now, we need to know that when we have a bigger area, the stress will be smaller, and we are asked about the maximum normal stress. So we need to take the smallest area in the bar BD so we can calculate the maximum normal effort. For this, we are going to take this portion of a bar where we can see the areas, and here, because in the bar BD the section with most stress is in the links, we need to take the area of the links. That will be this one right here, the area number 2. And for the bar CE, like the section with most stress is in the center, we are going to take the area number 1 here, that is the section of this bar. Now, knowing this, we can now set the formulas to calculate the normal stress for both of the bars BD and the bar CE. For the case of the bar BD, the formula will be in this way. Normal stress for the bar BD will be equal to the force in BD divided the area number 2, and for the bar CE, then the formula will be force CE divided the area number 1, this one right here. Now, we have the formulas, but and we have the information to calculate the area of each of the bars, but we don't have the force. So For this, we need to do diagram a diagram force to know how to calculate the force. For this, we have right here this that will be the diagram of force. We can see here the 20 kilonewton force upwards, and B, the force in BD, it's upward because of the tension, but because this is a balanced system, there is another force in this way, and that is the force that we have here. And the same for the bar CE. The force is in this way because of the compression, but because is another force that makes the balance system, this force will be this one right here. Now, having this diagram, we can calculate now the equation to find out the force.
How to calculate the force? It's simple. We just have to make a summary of moments. We have three looks and dimensions, which would be 0.24 meters and 0.4 meters. Now we must make the sum of moment around be equal to 0. This will be 20 kilonewton per 0.25 meters. This rotation is negative, leaving minus 22 meters because the rotation is the counterclockwise. Now we must calculate FIC 0.4 meters positive equal to 0. Now, how many coordinates do he have? Only FIC. This will be FIC per 0.4 meters, same and 5 kilonewtons per meter. Then we have to divide in 0.4 and in will be equal to 12.5 kilonewtons. Now, what is missing? The force FBD. Then we should summing force in 20 kilonewtons minus FBD plus 12.5 kilonewtons equals to 0. FIC equal to 12.5. Now we clear FBD and in would be 32.5 kilonewtons. The two results positive. This means that the assumptions that one for is in tensions and the other is the compressions is correct. Now we can calculate a force. The stress in the bar BG would be the half. This means that we should divide it in two. Now, to calculate R2, we must remove these area portions, equivalent to 0.036 meters minus the diameters, that is 0.060 meters, and the width, that is 0.08 meters. This means that the stretch of the sections FBD is 156 and 20, 5 per 10 to 6 Newton or square meter. This wants to say that the stretch in the BD bar is 100, each 50 and 622 megapascals, and its station is the positive Now, we hope with the streets in the var HC, which is in conventions. The weighted the streets on the var is, which is equal to 150,000, divided into half this 10.0030 and 6 meter for 0.008 meters. So the stretch in the HC bar is equal to minus 21.7 megapascals. It's negative because it is compressive.